Welcome to this explainer. Okay, I am so thrilled you're here because today we're doing something really fun. We are tearing down the engine and taking a fascinating journey deep into the structural anatomy of a vanilla JavaScript application. We're going to trace the exact step-by-step lifecycle of data as it travels through a code base, literally from the exact moment the script boots up to pulling down external data, rendering it right on your screen, and making the whole thing fully interactive. No bloated frameworks, no massive external libraries, just pure, unadulterated JavaScript showing us how the web actually works under the hood.
Now, before we even look at a single line of code, we've got to talk about a pretty massive roadblock. You know, every dynamic application out there needs a way to save user actions, right? Like, say, writing a comment on a post. Traditionally, you'd send that comment straight to a backend server, which writes it into a permanent database. But what happens if you just don't have a backend? What if you're building a lightweight front-end prototype, but you still absolutely need it to remember what your users are actually doing?
So the big question is, how do you build a database without a backend? How do you create a completely interactive application lifecycle using nothing but the browser? Well, modern browsers actually have this incredibly ingenious trick up their sleeves. They have their own built-in memory storage. And we can completely simulate a full-stack application lifecycle simply by hijacking the browser's local memory to act as our own personal on-the-fly database.
Okay, let's dive into this. Here is our chronological blueprint for reading and understanding the code's execution flow today. Number 1, booting up the app. Number 2, fetching the API data. Number 3, constructing the DOM. 4, mastering local storage. And 5, the interactive commenting logic.
All right, section 1, booting up the app. Let's see exactly how this thing gets started. Right when our application boots up, it establishes its foundational state using a few absolutely crucial constants. First up, we have our API URL. This points to JSON placeholder, which is just a fantastic free service we're using to grab some dummy demo data. Next, since we clearly don't have a real authentication system with logins and passwords here, we're just simulating a logged-in user by hard-coding a constant called currentUser and setting its value to the string John. It's super simple, but hey, it gives our app a sense of identity. Finally, sitting at the very bottom of our script file is the ignition switch. It's a single function call to loadPosts. Notice it doesn't take any arguments here because it just relies directly on that globally scoped API URL. Let's actually move to the next step and see how this builds, because mapping out the asynchronous timeline initiated by that ignition switch is pretty neat. Basically, the script runs and the app starts. Just milliseconds later, the loadPosts function is triggered. This sets off this whole chain reaction where the fetch API is called to reach out across the internet. We wait for a brief moment, and once the data finally arrives from the server, the displayPosts function is executed to handle the payload.
Moving right along to section 2, fetching the API data.
Let's zoom in on what's happening inside loadPosts. We wrap all of our logic in a try-catch block, which is super important to ensure our app doesn't fatally crash if a network request fails. Notice the async-async signature here. It securely handles the external data. We await the fetch to our API URL and subsequently await response.json to parse that incoming payload directly into a workable array of post objects. It's just a really clean, standard async execution flow.
Which brings us perfectly to section 3, constructing the DOM.
I absolutely love this part because JavaScript effectively puts on a hard hat and acts as a dynamic builder. The displayPosts function takes our freshly fetched array and just gets right to work. It locates the main app container, clears out any stale state by setting inner HTML to empty, and iterates through the data. For every single post, it dynamically generates a new div from scratch using createElement, assigns the necessary CSS classes, and injects it. It's literally generating the UI in real time based strictly on whatever that API payload gave us. All right, on to section 4, mastering local storage. Now, what's really interesting about this setup is the symbiotic relationship required to handle the data. See, the browser's local storage only accepts flat text strings. That's it. So our getComments helper function actually has to use JSON.parse to rehydrate those basic strings into a usable JavaScript array, and it gracefully returns an empty array if it's a user's first-time visit. Conversely, the saveComments function takes the array as an argument and utilizes JSON.stringify to pack it all back down into a string for storage. It's basically a continuous real-time translation layer. And finally, section 5, interactive commenting logic. Let's follow the exact execution flow of the add comment function signature. When our simulated user John clicks submit,
Step 1 immediately grabs the value from the input field and validates that it isn't just blank space. If it's valid, Step 2 calls our getComments helper to fetch the existing array from local storage. Step 3 is where the magic really happens. We push a brand new comment object into that array. Now notice that for the ID, the code actually uses date.now. Because we don't have a real backend database generating those unique sequential IDs for us, grabbing the current timestamp right down to the millisecond is a brilliant, lightweight way to generate a totally unique ID on the fly. Finally, Step 4 saves the updated array back to storage and calls renderComments.
And this brilliantly illustrates a core concept of efficient front-end design. Take a close look at the renderComments function signature. Notice it takes a specific post ID as an argument. Why? Well, because instead of lazily re-rendering the entire page every single time a comment is added, which would be a pretty terrible user experience, this does a targeted UI update. It filters the global comments array to find only the comments matching that specific post ID, and then isolates its update to just that one container's inner HTML. It is incredibly efficient.
So the crucial point here is the validation lock written into the edit comment function. We obviously want to allow users to update their thoughts, but we only want our user John to edit his own comments, right? Not anyone else's. Before allowing an edit, the code finds the target comment and runs a strict check. If the comment doesn't exist, or if the user attached to it isn't our global John variable, it throws a hard alert rejecting the edit. It's a localized client-side security checkpoint.
Which kind of brings us to a really fascinating architectural reality to wrap up on. We've just walked through building a highly functional, interactive application using vanilla JavaScript, and we used local storage to completely bypass the need for a backend server. It's fast, it's clever, and it runs entirely on the user's machine. But it also leaves us with a pretty massive question to ponder. Anyone who knows how to open their browser's developer tools can easily look right inside local storage and alter that data. So, given how easily accessible and editable client-side state is, what kind of sensitive information or real-world data should absolutely never, ever live here? I'll let you chew on that one. Thanks for joining me on this explainer, and keep exploring the code.